Hey learners, Jared here, and today we're going to try and bridge the connection between linear kinematic equations and rotational kinematic equations. And hopefully by the end you'll see that the two are kind of the same thing and are related by one key factor, and that is arc length. Let's take a look at a pulley with a mass hanging from one side. If that mass is released from rest, it will start to accelerate down. Now, the mass's acceleration is directly correlated to the angular acceleration of the pulley. The pulley can't accelerate any faster than the mass can fall, and vice versa. One can't accelerate faster than the other. If that happens, then that means there's slack in the string. Now, let's say the mass has fallen some distance d. That distance, that linear distance that the mass has fallen, correlates to an arc length's worth of string that was on the pulley. So the change in angular position, delta theta, is related to the change in vertical height of the mass, d. Typically you see arc length as S equals r theta, or arc length equals the radius of your circle times the angular displacement that arc carries out. So if I take my linear kinematic for the dynamics of motion of that falling mass, it has some acceleration, it was released from rest, and it accelerated for a certain amount of time. And I relate that to the angular position, or the angular change in position of my wheel. I'm going to divide the vertical displacement d by radius. Now doing that, if I divide over by radius, that's going to equal my angular position, or my change in angle for the wheel. And if I divide one side of the equation by radius, then I've got to divide all of the others by radius. And that's the connection, how you connect linear motion to angular motion. It's dividing by radius, specifically how far out that mass was attached when it started to fall, how far out that force is being applied, how far out the torque is on your wheel. Dividing both sides by radius is how we're going to connect that linear kinematic to the angular kinematic. Instead of relating change in height, we're going to look at change in angle, or the angular displacement of the wheel. And those rotational kinematics work no differently than the linear kinematics that we've been working with. There's angular acceleration now, there's angular displacement, and there's still time, angular velocity. All of those things are now just angular terms. What was your initial angular speed? How far did it sweep out in terms of the angle? What's the angular acceleration? All of those analogous terms are what we're going to use to describe angular motion, or an object that is rotating. Not an object necessarily going in a circle, but a rotating object like a bike wheel or pulley or cylinder or something along those lines. Thank you guys for watching how to connect linear motion to angular motion. We'll look into how does that angular motion amount to a certain amount of energy, and how do we calculate that next. And as always, keep learning.